Okay, guys, welcome back. We're going to look at the Jacaranda textbook for this one, simply because there wasn't anything in the Cambridge textbook that made you do it with like sigma notation or doing like a full sum with mathematical induction. So I want to do an example like this, and I've also included some questions down here. This one here is based off the example I'm going to do that have some sigma notation in it to also give you guys a bit of a different type of equation to do your mathematical induction with. We have actually done some questions with sigma notation last year in year 11 from this worksheet here. So this should still hopefully be a little bit familiar to you guys as well. So if we have a look here, you might notice it says it's from r equals 1, where this here is r. So if r is 1, then this is 1, 2, 3, 4, 5, up to n terms. So we can essentially just look at this as if it was n equals 1 to n is equal to 3n. For the sum of n equals 1 to n of 3n. The bit that's a little weird is that it's saying kind of like n equals 1 to n equals n. I think notationally, mathematicians didn't particularly love this. However, for our understanding, we can kind of think of this as more or less just being the exact same thing, where n is my term. So if I sub in n equals 1, I'll get my first term. N equals 2, I'll give me my second, 3, 4, 5, 6, etc., all the way up to n terms. It does have different letters on either side. You're going to find it essentially won't impact the overall problem. We still kind of solve these the exact same way. So I still want to do my first step, which is to test for n equals 1, or to test my first term. Now, in this case, when n equals 1, r essentially equals 1. So my left-hand side is going to be equal to 3 multiplied by 1, which is simply just going to equal 3. On my right-hand side, that is going to be equal to 3 times 1, 1 plus 1, all over 2. That's going to be 3 times 2, which is going to become 6 over 2, which also equals 3, which equals my left-hand side. I've tested for n equals 1, and it's correct. So now I'm going to go into my second step, which is my assumption part. So now I'm going to assume that n equals k. So that part still stays the exact same. Now, if I assume n equals k, then that means my sum becomes from r equals 1 to k now for 3r. That part's still going to stay the same. And that is going to be equal to 3k outside of 1 plus k all over 2. Now, for the k plus 1 step, it's going to look a little bit different, but it's still the same overall skill. So my sum now goes from r equals 1 to k plus 1, and it's still going to be 3r here as part of my sum. On the right-hand side, well, if it's k plus 1, that's going to be equal to the sum from r equals 1 to k of 3r. So this part here is going to still be here, just like with our normal proofs. And that's going to be plus, now I'm going to substitute k plus 1 in place of r, plus that's going to be 3 outside of k plus 1. This will equal my right-hand side, which will equal 3 k plus 1, 1 plus k plus 1, all over 2, which if you kind of tidy all of this up, what I'm essentially saying is the sum from r equals 1 to k of 3r plus 3k plus 1 is equal to 3k plus 1, and now it's going to be k plus 2, all divided by 2. Okay, I made a small typo here. I should write proof for n equals k plus 1. Just to summarize this whole process here, just to kind of make this r's and the k's make sense. Essentially, all I'm doing is I'm setting my sum up the exact same way I normally do. So I go from r equals 1 to n. Well, if n equals k, it's r equals 1 to k, and my 3r part is still going to stay exactly the same. That is going to equal the right-hand side, which if I now put k in place of n, that's simply going to give 3k, 1 plus k over 2, which is what I have here on this side. For the n equals k plus 1 step, I have everything up to k. So I have everything up to k, which is this part here, plus, if I have k plus 1, well, I'm simply substituting k plus 1 in place of r. I get 3k plus 1 over here. That equals my right-hand side, which again, if I substitute k plus 1 in, I get 3 multiplied by k plus 1, brackets 1 plus k plus 1. That simplifies to give this line. Okay, now like all my proofs, I want to establish my left-hand side and try to make that equal my right-hand side. or I can get my right-hand side and make it equal my left-hand side. But in this case, it's going to be easier to work with the left-hand side. So that means my left-hand side is going to be the sum from r equals 1 to k of 3r, plus if I substitute k plus 1 in place of r, I get this 3k plus 1. So my left-hand side is going to be this part here. I know that the sum of r equals 1 to k is equal to this part. So I can substitute this into my left-hand side, and that is going to equal 3k outside of 1 plus k over 2 plus 3 outside of k plus 1. So I'm now going to use my algebra skills to help rearrange this. Let's put both sides over 2, and this is going to equal 3k1 plus k plus 6k plus 1 all over 2. If I expand out and collect some like terms, that is going to equal 3k plus 3k squared plus 6k plus 6 all over 2. That is simply going to equal 3k squared plus 9k plus 6 over 2. 3 is a common factor, so this is going to be 3 outside of k squared plus 3k plus 2 all divided by 2. If I factorize that, that's going to give 3 outside of k plus 1, k plus 2, all over 2. If I now check, because that's about as factorized as I can get, if I check, that is in fact equal to my right-hand side over here. So that's going to equal my right-hand side QED. So to make my final statement, therefore, shown true for n equals 1, assume true for n equals k, and prove true for n equals k plus 1 by mathematical induction.